Okay, so let's look at curve sketching again, and let's see if we can't streamline the process just a little bit. So with these problems, you're going to be asked to graph y equal f of x without just going to the calculator to do it. And this is because sometimes going to the calculator, you can't, if you don't already know what to expect, what you see on the calculator may not even come close to what the complete graph of the function would be, okay? So just want to remind you that if you solve f of x equals 0, okay, what you're finding there would be the zeros of the function. Okay. All right, so zeros of the function. So that's the places where your function is going to cross the x-axis. So you're really finding the x-intercepts, okay? All right, and then if you know the x-intercepts, then that means you can test all the, like if this is the x-axis and you know the x-intercepts, then you can test these intervals to find out where the function, so where f is above or below the x-axis, okay? All right, now where calculus comes in is you're going to want to find where the first derivative equals 0 or where it's undefined. Okay, so this helps you to figure out where you're going to have possible maxes and mins. Okay, these are going to be you'll be finding the critical points, and these are going to turn out to be possible maxes or mins, extreme values. Okay, so for instance, where the function's equal to 0 would be where the horizontal tangent line, where you would have a horizontal tangent line. So the slope would be 0. And then the undefined can be a max or a min because you might have a cusp or something at that spot. So the first derivative wouldn't exist, but you'd still have a maximum value there. Okay. And then those possible extrema are going to wind up, those highs and lows that you see are going to wind up cutting the plane into intervals. And the intervals there are going to be where f is increasing, where the original function is increasing or decreasing. Okay. And so we're always trying to get information about what f would be like. Okay, so if you're doing the first derivative, it helps you to figure out where you're going to have the maxes and mins and where the function is increasing or decreasing. Okay. All right, the second derivative, that's going to give you what we call possible inflection points. Okay. All right, and that is going to help you to determine where f is concave up or concave down. Down. Okay. So inflection points, they look kind of like, oops, my hand slipped. Like that right there, you'd have an inflection point. So it's where the graph changes from being concave up to concave down. Okay, so concave up would be when it looks like that, only you don't necessarily have the whole entire curve. Concave down like that, but it could be just a piece of the curve. Okay, increasing means f is going to be going up. It's not necessarily going to be going up like a line, but it might be going up like that. And it can be wavy, and then decreasing, but it could be wavy. And then the setting the original function equal to 0 just tells you where it crosses the x-axis. And then you can use those x-intercepts to break your plane into intervals just to see where the function is above or below the x-axis. All right, so those are the three main ideas. And so I also included on this page, there were some graphing guidelines in the textbook that are kind of like the template, but it just seems less time consuming. So I thought it might work for us just to use those graphic guidelines and see what happens. Okay, so I want to do one example with this, and then we'll go through and I'll do the examples on that other sheet. So let's suppose we have something like, let's take maybe a parabola. Okay, so let's say we have something like, let me get a good one. Let's just do a simple one. All right, so let me go to a new page, and let's suppose we want to kind of go through and sketch the graph of y equals x squared minus x minus 12. Okay. All right, now you should already know quite a bit about that one, but I just want to go through these guidelines here. Okay, so first off, guideline number 1. Okay, guideline number 1 just asks us to think about what are we going to try to graph? What's the domain, or where do we care about seeing the graph? So this is a polynomial. It's actually going to be a parabola, so the domain is going to be all reals. Okay. So all reals from negative infinity to positive infinity. All right, next we can take advantage of symmetry if there is such a thing. But for symmetry, this is something you can choose not to do. What you do is you plug in negative x for x, and you see what happens. So if I put a negative x where x is, and be real careful about your signs, this would still be x squared, but this would become plus x. Okay. And if what you get, if this right here, does it equal f of x? Does it equal what we had originally? No. Does it equal the opposite of what we had originally? Well, no. Okay, so it doesn't have either y-axis. This would be y-axis symmetry. It'd be symmetric about the y-axis. And this would be origin symmetry if this happened. Symmetric about the origin. So it has neither of those. Okay, so it's really an easy thing to do, but you can get through this without doing that. Okay, the third step says go ahead and get the first and second derivatives. Okay. And then after we do that, we'll look for the possible critical points and inflection points. Okay, so let me go ahead and do that. So this is step 3. We're looking for f prime of x. So let me just think about, or I'll call it y prime. Actually, let me go back up here and just call it f of x. Okay, so now I can talk about f prime of x, find out where that equals 0. We already know this isn't undefined anywhere. Oops, still 3. And then f double prime. Okay, so this is just a nice polynomial. So f prime of x, oh, before we set it equal to 0, let's just do each derivative. F prime of x would equal 2x minus 1. Okay, and f double prime of x, the second derivative, would equal 2. Okay. Then step 4 says use that information to find points where f prime is equal to 0 or undefined. So you're going to take 2x minus 1 equal to 0. This is step 4. Okay. See where this equals 0. Okay. We know it's defined everywhere. So the only critical point happens when x is 1/2, because we could add 1, divide by 2. All right. And then the f double prime never equals 0. And it's also never undefined. So no inflection points. We know that. It's not going to change from concave up to concave down. There aren't any inflection points. Okay, but we know we have a possible extreme value at x equals 1/2. Okay, so then that's the only one. All right, so let's go back and check the guidelines since it's the first time we've used them. All right, so we find the critical points and possible inflection points. We did that. So now we're going to use that information to determine intervals where the function is increasing or decreasing, and then also where the function is either concave up or concave down. Okay, and then we'll go back and we'll identify this 1/2 right here. We'll make it a point and we'll say whether it's a max or a min after we do that. Okay, so what I'm thinking about here is there's only this one critical number. And if I pick a value on the left and a value on the right, I can determine whether it's increasing, decreasing. That's what the first derivative will tell me. So if I plug 0 into the first derivative, I'd wind up with 2 times 0 minus 1, which would be -1. So when I'm right there at plugging in a 0, I'm going to get a negative. Okay. And when I plug in a 1, I'm going to get a positive. Okay. So that's what the first derivative values turned out to be. Okay. What that tells us is when you're in the interval from -infinity to 1/2, and then when you're over here from 1/2 to infinity, okay, when you're from -infinity to 1/2, the function is going to be decreasing, not necessarily in a straight line, but it's going to be falling. And then when you're from 1/2 on, it's going to be rising. Okay. Now you can use that to determine that 1/2 something is a minimum. Because you know f, this is what f is going to look like. It's going to be decreasing and followed by increasing, which makes that point a low point. You see it? Okay. All right, so we're going to need the y coordinate of that point. Now this is where, to get this, you're going to plug 1/2 into f. Okay. So you're going to go back to f, and you're going to say, all right, well, f of 1/2 would equal, remember the f function was x squared, so that's 1/2 squared, minus x, minus 1/2, minus 12. So you're going to plug that in and get the y coordinate of that point. So that's 1/4 minus 1/2 minus 12. So that's -1/2, nope, -1/4 minus 12. So that equals -12 1/4, which is -48 49/4. Okay. I like the mixed number when I'm trying to think about where it is on the graph, but a lot of times what they'll want right here. Now we can go put it. Let's go put it right here. We just found that, and that means the y coordinate of this point is -49/4. Okay, and we know it's a minimum because it was decreasing and then increasing. We also know it's a minimum because of the second derivative. F prime of x can't be 0, right? F double prime. F double prime equal 2. It was positive. So what that implies is that it's going to be concave up everywhere. So because of that, I actually know it's going to be concave up everywhere. And then this is going to be the low point, okay, or the vertex of that parabola. Okay. All right, now that's the gist of the first and second derivatives. But to know where that parabola is located in the coordinate plane, you might want to know the zeros of the function, and which would be the x-intercepts and that kind of thing. All right, so we're down to number 6. Number 6 was when we actually figured out it was a minimum and all of that. Okay, so this is really 4, 5, and 6 up to here. Okay. All right, so let me do it over here. So now in 7, I'm supposed to be checking on asymptotes and end behavior. All right. So for asymptotes, there are no asymptotes. Because it is not undefined anywhere, so there's no vertical asymptotes, and there's no horizontal ones. If you looked at what happens as x approaches positive or negative infinity, what you'll find is that the function points up on either side. Okay, so the end behavior was the other thing to consider. We can get that from the leading term, which was x squared, and that tells us at the ends it's going to be opening up. Okay. All right, so that's asymptotes and end behavior. Now, this finding the intercepts is going to help us just get this thing pinpointed in the coordinate plane in the right spot. Now, in my guidelines, that was one of the first things we did. But this one, you do all the first and second derivatives first, and then they have you do it. Okay, so let's go ahead and get our intercepts. All right, so for the y-intercept, okay, that's 0 something. So you're just going to take your function and plug in 0. So 0 squared minus 0 minus 12. Okay, and so the y-intercept is negative 12. Also, on parabolas, it'll just be that constant term. So when we get ready to graph, we know that. Okay, and then the x-intercepts, they're a little harder sometimes. This one won't be bad, but sometimes they can be kind of challenging. You want to find out what causes the function to be 0 because it's their points that have a y coordinate of 0. So you just factor, this one factors into x minus 4, x plus 3, set those equal to 0, and you're going to get that x equals 4 or x equals negative 3. So your x-intercepts are at 4, 0 and at negative 3, 0. Okay. Now that information is going to be put together with the fact it's concave up. We also know the minimum value. We can get everything plotted real well. Okay. All right, and that's the last job is now choose and get this thing graphed. So we're going to do it by hand, and then you can check by graphing on the calculator. Let me do the graph right here where I already have that. So basically what I know is this is going to be negative 4. Nope, negative 3. Negative 3. And over here is going to be positive 4. So your y-axis is going to do something like that. This y-intercept right here, okay, that's going to be the point 0, negative 12. Okay, so this is going to happen at negative 12. Okay. 0, negative 12. This is negative 3, 0. This is positive 4, 0. Okay. And then the vertex, the lowest point, happens over here at 1/2. So it's like right here, you're going to have, an axis of symmetry. And that point right there is going to be that point 1/2. And then the negative 12 1/4. So it's going to go a little below negative 12, but just barely. And that's all the important features of the graph. Okay. All right. So that's probably overkill for a parabola because you kind of already know a lot about parabolas. But if we take the intercepts, the max or min, and we think about increasing, decreasing, and concavity, we can get a pretty good sketch of just about anything. I'm going to work through some examples in my next videos.